Hi, this is Shreshi. I'm a student of MSc Cybersecurity, and during this video, I'll give a brief about my project on improving data protection in Internet of Medical Things using blockchain and secret sharing method, and demonstrate the implementation of the proposed model. Agenda for this presentation is run through the project objective, provide introduction and background about the project, take you through the proposed architecture, give an experiment demonstration, talk about results and limitations and future work along with the conclusion. The objective of this project is to use blockchain technology and IPFS storage along with secret sharing algorithm to address medical data protection issues in external cloud services and improve data integrity and privacy by designing a distributed system. Now, to give a brief introduction, IoT devices are now becoming a critical part of healthcare ecosystem. The basic IoT architecture consists of three layers: physical layer, which consists of IoT devices like wearables and sensors. Then we have information integration layer, which consists of databases that is used databases and servers, which stores and processes the data. And then we have application service layer, which consists of user application that provide continuous monitoring. Now, these devices have several benefits, including remote monitoring, improved disease management, enhanced experience to the patients, and so on. Having said that, these devices have shortcomings in terms of computational capabilities, access control, data security, communication protocols, and storage issues. Now, multiple approaches are now being established and researched to overcome these challenges, such as cloud-based architecture, which helps to overcome data storage and computational issues, but it has its own set of challenges such as resource sharing, lack of confidentiality, lack of influence, lack of isolation, and lack of processing information of the CSV. Now, then we have blockchain-based architecture, which helps to maintain the integrity and accessibility to the empty data, and it uses distributed ledger to achieve this. Now, in this project, I intend to provide a model to overcome the privacy and integrity issue of storing confidential data with public cloud service provider and safeguarding it from the misuse by cloud service provider or by any external adversary who might compromise this cloud services. Now, the proposed model builds a secure IoT architecture using blockchain technology and CSV and along with secret sharing algorithm. It uses the secret sharing algorithm to split the data into multiple pieces and store it in distributed cloud storage that uses IPFS storage to ensure that not a single CSV has access to all data pieces, and use blockchain to maintain the integrity and access of the data. So the core component of this model is secret sharing algorithm, which was originally proposed by Adi Shamir to protect cryptographic keys and is also known as KN scheme, where n is the number of data pieces that is split with polynomial equation of k minus 1 degree, and k is the threshold defined as minimum number of data pieces required to reconstruct the original data using Lagrange's interpolation formula. Now, this particular algorithm divides and distributes the data pieces to multiple CSV and can also reconstruct the original data even with fewer number of pieces. Now, if you see in this data flow, when the original data is generated by IoT devices, it moves to a layer called internetwork layer, which is in the private domain of the user. Which is responsible to generate random prime numbers in order to implement secret sharing algorithm to split the data into multiple pieces. Now, these data fragments are then dispersed to um, cloud service providers after encryption, and the transactions are recorded in blockchain. Now, whenever there is a request to access these data, the request flows through the blockchain, which is used to fetch the data from the IPFS storage and then decrypt it, decrypt each pieces, and then reconstruct the data using Lagrange's interpolation formula to generate the original data. Now, overall, this particular model has four layers. The first one is IoT layer, which has wearables and sensors to gather data. Then we have internetwork layer, which is in the private domain of the owners, the device owners, basically, and is responsible to implement a secret sharing algorithm, generate private keys to upload the data to on the IPFS storage, and it also has the blockchain wallet. The next layer is fog layer, which consists of blockchain in order to support the integrity of data. And finally, we have cloud layer, which consists of IPFS storage to provide a distributed storage. Now, benefit of this particular approach is that it provides a solution for privacy using decentralized multiple cloud services. And the proposed algorithm can recover the original data even if a particular CSP modulates or loses the data, and can use blockchain to verify the integrity of data stored by the CSP. Now, having said that, I'll just quickly take you through the model overview. So if you see here, this particular model consists of multiple components, including the IoT devices. We then have data manager, which is based upon the smart contracts, and uses smart contracts to verify and validate the users and the devices. And it is connected to blockchain, wherein the hash value of the data being uploaded are stored along with the hash value of the storage location that is produced by IPFS storage. And then we have cloud service providers, which are nothing but IPFS storage basically. Now, if you look at the data flow diagram, the data manager is at the center of this particular model. And whenever it receives a data upload request, it uses the admin, which is based on the smart contracts, to verify the devices and the patient details in order to upload the data. So only if a device is allotted to a particular patient, the data can be accepted, and it would go through the secret sharing algorithm in order to upload it on IPFS. So once the verification is done and the secret sharing algorithm is applied, the data pieces are uploaded on IPFS storage. And these IPFS storage systems then shares the unique ID, hashed ID, which is stored on distributed hash table, and is also maintained on the blockchain for the future verification purposes. And whenever there's a request from an end user to access data, the data manager is responsible to verify the patient details and then apply the Lagrange's interpolation formula on the data retrieved from IPFS based on the IPFS address fetched from the distributed hash table. Now, this slide talks about the data uploading and sharing data flow. So when the data uploading starts from the mobile gateway and there's a transaction request using the user interface, the request moves to the blockchain client, which initiates the data manager, who is then responsible to verify the patient and device ID using the smart contracts. Once that is done, it applies the secret sharing algorithm, spreads the data, and upload it on IPFS storage, which sends the hash ID back to the data manager. And this hash ID is then updated on the transaction pool along with the hash value of each data pieces. So if you see here, each block of the blockchain consists of block ID timestamp, the hash value of secret data, like each secret data pieces. Then we have CSP ID, which is also encrypted. And then we have encrypted IPFS hash ID, because this is also public ID. And then we have patient wallet ID. In order to identify a particular patient, we are using their blockchain wallet ID. And then we have device ID, which is also in the encrypted format. Now, the same blockchain network is also accessible by the end user who wants to access the patient's data. So whenever there is a request to access data from the end user, the request from blockchain client goes to the data manager, who then verifies the patient detail using the smart contracts, fetches that data from cloud services based on the distributed hash table, and then validates all the information based on the blockchain data. And if everything is okay, it applies the Lagrange's interpolation formula to reconstruct the data and sends it back to the end user. Now I'll quickly run you through the demonstration of the application, which is based on Solidity and JavaScript. So this is my user interface where I upload the data and retrieve the data as well. This is the smart contract for device registration, where we have functions to set the device registration, remove the device registration, along with device registration status check whether a device is registered or not. And then we can also encrypt the device ID. So the idea is to store the encrypted device ID on the blockchain. Hence, we are putting an option to encrypt the device ID. Similarly, we have patient registration smart contract, where we have option to set the patient registration, remove patient registration, and similarly we have encrypt patient ID and check patient registration status. Then finally we have patient device data encryption smart contract, where we have option to engage the device to a particular patient um, using set patient device registration. And we also have option to remove patient device registration, as in a particular device could be removed from the patient and can be allocated to somebody else as well. And then we have options to upload the data to IPFS. We have functions to remove the data as well from IPFS. Okay, and I'll quickly take you through the data that I'm going to upload. So this particular Excel sheet consists of a data sample. So this is the wallet address which identifies the patient. Then we have the IoT device ID, which identifies the device, and then we have respiration rate and body temperature. That is data that is being retrieved from our IoMT device. So when we go back here, the first thing that we have to do, we have to register a patient, and then we have to register a device, and then upload the data, so that when the data is being uploaded, the device is allotted to the patient using that particular application. So we'll check if the device is registered or not first. It says false, as in the device is not registered. So we'll have to register the device. So when we try to register the device, we will see that MetaMask gives us option to select the transaction time, which will also change the fees that will be required for the transaction. As in, if we want a faster transaction, that gas fees will be higher than the slower transaction rate. So right now I'll just keep it the way it is, and I will go ahead and confirm this transaction. I'll check the status of transaction. It's still pending. In the meantime, I'll quickly copy the patient ID as well for the patient's registration. And I will check if the patient is registered or not. The patient is not registered. I'll go here, connect to Web3. So the device registration is done. I'll check if the patient registration is done. So this is also done. Now I'll quickly go here. So this section asks for secret key that will be used to encrypt the data fragments while being uploaded on IPFS storage. So I'll just give some random keys. And I'll select an image file to upload it on the IPFS network. I'm using NFT.storage for storing my data. So I'll add, oh sorry, I'll have to first select a image file. So to store the data on NFT.storage, I need an image file. And then I'll have to select the file for uploading the data. So this is the original file that is being uploaded. So once the uploading is done, like once the data is split and uploaded on the IPFS, I will get an option to upload the detail on blockchain over here. So I will now click to upload on the blockchain, and I'll have to approve all the transactions. So this particular application then goes to patient device data encryption smart contract and runs this in order to upload the data. So I can see all the transactions here. So here I can see that there's a transaction that is happening. Let's just quickly refresh it to see if it is approved. So for every transaction, I'll have to put an approval over here in MetaMask. So because there are 4 pieces of data that is to be uploaded, so I get 4 requests for the transaction, along with 1 request for allotting the device to the patient ID. And in this case, I'm using 2 IPFS storage, one as the primary and one as the backup, and hence I get in total 9 requests for uploading the data. So here, if you could see the first request that came for set patient device registration, and then we had upload patient data to IPFS1 and IPFS2. Then again upload patient data to IPFS1 and IPFS2, and store parts of Y. So this function uploads the pieces, data pieces on IPFS, and then this function stores the hash value of Y on the blockchain. Now going back here, since all the transactions are now done, I can retrieve the data, which will then apply Lagrange's interpolation formula to retrieve the values. Now, one of the limitations that I faced with Lagrange's interpolation formula is that it worked well with the numerical values, but if I tried to upload or give some text value to it, I was facing certain challenges. So here n value is 4 as the data is split into 4 pieces, and k value is 3 as in we need at least 3 pieces to reconstruct the data. So I can use any of these 3 secret keys to retrieve the data, as in any of the 3 storage of IPFS or the data pieces that is stored with IPFS can be used to reconstruct the original data. So suppose I'll have to first select the index that is 0, suppose I say 2 and 3, and I'll give 111. I'll give the respective keys. Then 4. And then I'll have to put the patient ID, which I can fetch from here. I'll get data. So I'll get the respiration rate here, which was 90. And then similarly, I can reconstruct the data using other 3 for the next one. Suppose 1, 2, and 3. So here I'm getting the body temperature as 88. So with this particular experiment, I just wanted to show that how we can split the data, store it on the IPFS storage using secret sharing algorithm, and how we can retrieve the data using Lagrange's interpolation formula with n is equals to 4 and k is equals to 3. Now going back to the presentation, a few experimental results that I would like to share with you now is the data, the time that we noted for splitting the data using secret sharing algorithm is fraction of microseconds, especially more because the data size is lower. But if you see it from the time to upload it on the IPFS network, you will see that it is much higher than the time taken to split the data. So there's a higher overhead because we are going for uploading multiple pieces on the IPFS storage. And then time to download the data is again very less when compared to upload the data. And moreover, we can see that the gas consumption for registration and device allocation increases as and when the number of devices or the number of registration increases. Here, I'm just trying to show the time taken for transaction impacts the transaction fees. If we want to have a faster transaction, we'll have to pay higher fees, and this may vary from network to network. Here, I'm using Rockton network, Rockton Ethernet for this particular deployment. And then every activity has a different gas value, like we have device registration, patient registration, device allocation, uploading data, that is uploading 4 pieces of the data, and then recording hash of the data to blockchain, then deleting the data. With that, I would like to quickly talk about the limitations and future work. In terms of limitations, the first one that I came across was overhead. Now, since here we are using single data, since here we are using a single data which is split into multiple pieces, and it directly impacts the time consumed to split it and upload it. Now, if we are going for a larger data set, it will be even more, it will increase the time consumption and the gas usage as well. And hence, I would recommend that extend the experiment to try and upload entire data set to check if, to verify if the time consumed or the gas usage is lesser. So going ahead for threshold, because we have defined a particular threshold, that is the minimum number of pieces to reconstruct the data, an adversary or CSP cannot retrieve the original data only until the number of pieces is less than the threshold. As and when they get the number of pieces equal to the threshold, they can retrieve the data. Another limitation that I faced was that I was using free version of IPFS storage, which limits the amount of data that I can upload at one time. And hence it would be beneficial if this particular experiment is conducted with a paid version of IPFS storage to understand the real-time performance in terms of transaction time and gas usage. Further, in terms of access control, we have enabled data uploading on IPFS by using synchronous encryption that is done via secret key, but we have not focused on end-to-end access control. In future, we can also integrate access control mechanism in this model to ensure that the secret key is distributed in a secure manner to the authorized individuals only. Now, to conclude this particular session, I would like to say that in this paper, we analyzed the requirements of safeguarding IoT data in a larger ecosystem and protect it from CSP as well as external adversaries. We proposed a blockchain-based IoT architecture with distributed storage to improve privacy and integrity of IoT data when stored on a public cloud server. This particular model helped to improve the privacy by using secret sharing algorithm, helped to improve integrity by using blockchain. It also provides distributed storage structure by using IPFS storage, and it finally reduces the risk of data loss and compromise. That is, in case a particular CSP is compromised, only a piece of data is lost and original data cannot be retrieved by the adversary or the CSP. Moreover, even if we lose a particular piece of data, the original data is not lost because it can be reconstructed using lesser number of data. So that is all from my end. Thank you for going through this video. Let me know if you have any questions via email, or you can connect with me on Teams. And if you need any further clarification, I'll be happy to arrange a call for this. Thank you.